0.75 in this room, but a few years ago. Fourier transforms? One year I told the students I'd try to answer any question they'd ask if I could. And so they actually started asking me questions from their mechanical engineering course. It took me about 2 weeks to figure out that I was just being asked questions from their homeworks from their other course, but that's right, I didn't mind answering. But you have to remember that the answers change depending on the professor who's teaching it, right? We talked a little bit about fatigue. Maybe I'll start with this. I will now tell you how to do your own failure analysis on any fatigue part. All you have to do is have this little chart, which was developed 20 or 30 years ago by someone. It's in the Metals Handbook. It's in a bunch of fracture handbooks. But it helps if I focus it, I guess. I can't focus the whole thing. But what I have here is I can have different amounts of stress concentration on a part, and the stress concentration would be a notch. And so this part right here has no notch. This has a gentle notch, and this has a sharp notch. Over here I go no stress concentration, medium, and high. And across here I have high nominal stress and low nominal stress. I'll talk about stress concentrations a little bit in a second, but let's just kind of go down here. So this would be a cylinder under high nominal stress with no stress concentration. The fatigue crack will initiate on the face of the bar somewhere like this, and you'll have these little striations running from here. You can actually see little lines on the fatigue sample. If it's a rectangular sample, it might look something like this. Actually, I could have brought one of those in. Maybe I'll bring one in tomorrow, but these are some aluminum wheels that are fatiguing off on automobiles. But anyway, and it looks similar to this, okay? It turns out there's not a big stress concentration. It's a fairly high nominal stress, and it is a rectangular part, and it looks something like this. Now, some of them start at a corner. This is tension, or tension compression for all of these. Down here, you're going to have unidirectional loading from one side. Here you have reverse bending, okay? So you're going to actually have a fatigue crack start on this side and also on this side, and they grow together here in the center, and this would be in torsion, okay? And without going through each one of these, each fatigue crack will have a different pattern. This is high nominal stress. You notice the large final fracture area of this guy? Whereas over here at low nominal stress, you have, actually on low nominal stress, well, let's do this one, because that one, they don't even leave much of anything to see where the final fracture is. Here you have a large final fracture area over half of the sample. This is a very small fracture, okay? And there's all kinds of things you can say about these things. First of all, I told you at the last class that typically you won't get fatigue unless you're above about half of the yield strength of the material. Well, this is high nominal stress. The final fracture is greater than half of the sample, so the nominal stress was probably about greater than half of the yield strength of the material. And so you can expect a fatigue crack to start there. But how can I explain a crack starting here with no stress concentration but low final fracture? Because this is maybe only 20% of the final cross-section. How did that fatigue crack initiate? They're not supposed to initiate if you've only got 20% of the stress. That means there was some unusual event that caused it to initiate. Okay? It doesn't usually see high stresses, but the fatigue crack initiated, so it must have seen a high stress or an impact or something in its previous life. Okay? Whereas over here, it's at high enough stresses, you can expect that eventually it's going to fatigue. So this is the type of failure you see in most medical implants. You know, you have some spinal fusion or something, and they put some implant in your spine to hold things together. It turns out the metal bars and screws and things they put in your spine if you have a spinal fusion are not going to last as long as bone. Bone is a living material, and it repairs itself as it goes along. It's self-healing. and it grows new cells. And as it wears away, it rebuilds itself. Metals don't do that. And the metals also have very, very high stresses on them because they're very stiff compared to the bone. If you have a very stiff component in a structure, much more stiff than the rest of the structure, well, where do the stresses concentrate? In the stiff component, right? So the metal, they actually call it the implant race. When they try to do a spinal fusion, they go in there and they take a file and file away the end of the bone, so you get rid of the regular bone that's there, and you try to squeeze these two bones together and hope that they will grow together. The surface of the bone has, it's not a skin, but it has a different type of bone on the outside, so they have to abrade the surface, get rid of that bone, because ordinarily two pieces of bone don't want to grow together. At least that's good, right? Because otherwise you wouldn't be able to bend over, right? Or move your arm or anything. But if you do want two pieces of bone to grow together, you have to abrade the surface so you get down to the bone underneath, and that bone will grow into another bone. So they go in there with a file. Isn't it great? I got some videos of this if you want to see it. On real people. Okay, mostly all you see is a lot of blood. But anyway, they go in and they scrape it, and then they use some screws or some wires or rods or whatever. And while you're healing over the next 6 weeks to 6 months, the metal is supposed to bear the load. But over time, the bone is supposed to grow together and start to bear the load. And in 5 cases out of 6, the bone does grow together and starts to bear the load. And after 2-3 months, the metal's not being loaded at all anymore, because essentially this fusion has taken place, and the metal's just, you can go and take it out in another operation if you want, which sometimes they do. But sometimes, particularly if someone's a smoker or gets too much exercise while this is healing, it doesn't grow together, and the metal has to keep a high load the whole time. Instead of the load on the metal decreasing with time, it just stays there, and eventually in 4, 5, 6, 7, 8 months, depending on the loads the person puts on the metal's going to fatigue and break in two. And in 1 out of 6 cases, you don't get a successful bone fusion, and in a number of those cases, the surgeon will leave the thing in there and the thing will break, and the people get all upset and say this wasn't supposed to happen and stuff. Well, anyway, can you figure out why, if you're a smoker, the bone doesn't heal? Bones don't grow together as quickly? I had to read it. So, when you smoke, there's less oxygen in your blood. Turns out in order to grow bone, you need oxygen in the blood. And so, if you're a smoker, you just decrease the total oxygen in your blood, and therefore your bone doesn't heal as well. Nothing heals as well if you're a smoker. It takes longer to heal. So, anyway, so the point here is, if you're experienced at looking fatigue fractures, you can just kind of look at these things and you can say, well, the load on this was reverse bending, or it was torsion, or it was whatever. It's a high nominal stress or a low nominal stress. It had a stress concentration, or it didn't have a stress concentration, or in a case like this, there wasn't a stress concentration. And the difference here between stress concentration and no stress concentration is no stress concentration you get from the origin, kind of circular striations. With the stress concentration, they become more flat, and with a very high stress concentration, they essentially change their orientation. You actually will have multiple origins. Typically, on something like this, you'll have a single origin, and everything grows from it. On something like this, you may have 100 origins around here because they're all originating at the stress concentration. When you don't have a stress concentration and you don't have high stresses, it usually initiates at some defect or something. So this either had a defect. If I can't find a defect, then it saw some unusual stress somewhere in its life. In fact, one way to think about failure analysis in general, something can fail because of a defect in design. It can fail because of a defect in material. It can fail because of a defect in manufacture or assembly. Or it can fail because of abuse in service. Or it can fail because of a combination of these things. Okay? So you're going to look for defects in the material in that low stress fatigue fracture. If you don't find that, then you basically have to assume there's some sort of abuse in service. Defect in design, if you see something that's really highly loaded and it's not supposed to be highly loaded, well, that's why it failed. Turns out the implants, medical implants, no matter what you do, they end up being highly loaded because there's just not enough room in the human body to put enough metal there to support things. In any case, there's lots of things you can tell. I remember once 20 years ago, a nuclear power plant sent me some bolts that had broken in two. And one of the first things you should do is try to get a history on the part. And I called them up, I said, so where were these operating? And they said, we're not going to tell you anything about it. We want you to tell us what you could say as a metallurgist by looking at it without any prior history. I said, okay. So I went and I looked at it, and I told them that it had operated between 400 and 600 degrees Fahrenheit. It was a fatigue fracture. It had had several very severe loads, big impacts, and that its normal operating stress was very low. And they said, how did you know that? Well, the final fracture was small. Oh, I also think I told them there was no stress concentration, okay, from the shape of the, kind of looking at this stuff. And I could tell that I also told them that it had been in operation, this failure had occurred over a number of weeks, but not necessarily years, okay, just by looking at the surface. Well, how did I get the time and the temperature? The time and the temperature came from the fact that steel, when it is heated to different, as you increase the temperature up to about 400 degrees, it starts to get a straw color, starts to get a little brown color to it, if it's nice fresh steel, which a fracture is. And if you go to 600 degrees, it actually gets a blue tint to it. And in fact, there's something called blue brittleness. And in fact, I analyzed the steel. It was a carbon steel susceptible to blue brittleness, and that was one of the reasons. And I said, but there is some big impact load on this. It turns out they had a water hammer in their plant. And they knew that, but they weren't going to tell me that. But I could tell from the material. And it turns out, yes, this thing was in a steam system. It wasn't a water hammer, but they had a steam hammer, or whatever. It had a hammer in the piping system. And so they were very impressed, and so they sent me another sample and actually told me the history on that one. But this was just a test to see if I could tell them what was going on. Now, stress concentrations. Most of you probably in here, having worked in the real world, know what a stress concentration is, right? We're not talking about emotional stress here. We're talking tensile stress or compressive stress. But basically, whenever you have a change in section, going from one thickness or diameter to another, there's going to be a change in stress. And in fact, you can draw the stress lines, and the density of the stress lines tells you something about stress concentration. Whenever you turn a sharp corner, those lines are going to get closer together. If you really want to know, since we're sitting in a math classroom, if you really want to know, if you solve Laplace's equation, okay, if you have a good feel for Laplace's equation, you will find that things bunch up around corners. Whereas if you solve Laplace's equation in something that's gentle, you'll find that they don't bunch up in the corner as they go there. That you can have a nice kind of continuous change from high stress to intermediate stress without everything trying to turn around the corner and get bunched up around the corner, right? You kind of see how things get bunched up even tighter around the corner than they would be here in the higher stress region. Whereas here, they're not bunched up as much. You just solve Laplace's equation in concept in your mind. Okay? That's all it is. Laplace's equation is a potential field. And what a potential field tries to do is spread out as uniformly as possible, but if it spreads out against the sharp something, everything bunches up against that. Okay? If it was a knife edge, if you lay down a sheaf of papers on top of a knife edge, you'd have a big stress concentration right there at the knife edge, right? But it would die off to the side. If you kind of learn to visualize that, you don't have to solve Laplace's equation, you can just estimate it. So anyway, this is actually a plot of the stress, and you get a stress here and a stress here, but you get a big sharp stress here, and you can decrease that concentration over here. This is a head of a bolt showing the stress concentration, just a bunch of different geometries. Whenever you have a change in section, and just like I showed you the book on fracture mechanics, there are whole books. Also, this is only in the 2nd edition, but this book goes back. This goes back a long time because people don't do stress concentrations anymore. This was the way they dealt with things back in the 40s and 50s. This particular edition is copyright 1997, but the original version of this was 1976, but which I have if you want to see the first edition. But nonetheless, stress concentration factors, a wonderful little book with graphs. Oops, full of graphs, all kinds of geometries of stress concentration. Most of them, well, some of them are mathematically derived, so here's a notch in a plate, and they'll be under tension or torsion and things, and it'll have different radii of curvature and things. Stress concentrations and stress intensities are not the same thing. They don't even have the same units. Stress intensity, K, has units of KSI square root of inch, whereas stress concentration is basically a multiple of stress. If I have a very sharp corner with a radius in here of 1 mil, thousandths of an inch on a shaft 1 inch in diameter, I could have a stress concentration of 5 to 10 times. Okay, so my nominal stress may be 10 KSI, but I could have 50 KSI in there. That could well put me into the range where I get fatigue cracking. And so that's why you get cracks and keyways and things like that. If you have a gentle thing like this, your stress concentration may be 1.4. You get a 40% increase in stress. No big deal. Within the error of the analysis in most cases. So you don't want sharp changes, you want gentle changes. It is possible to go back and even if you don't have enough information to do stress intensities, to kind of look and say, well, how sharp was the notch? Could it have raised the stress to a high enough level to cause fatigue? And I've done it dozens of times, and it's amazing how well it works. Okay, you kind of go back and you say, well, gee, I need a stress concentration of 3 to get me to a stress level high enough to cause fatigue. I have fatigue in the part, and I go and I look at the radius, and I look in here, and I find, lo and behold, I got a stress concentration of 3.5, according to the book. So of course I got a fatigue crack. By the same token, you find some people say, oh, it's a stress concentration, and you go and you look in the book and say, no, it's not a sharp enough radius. I mean, you can quantify it is the point. Most people are not quantifying things. They just say, oh, there's a stress concentration there, that's why it failed. Oh, I saw an inclusion there, it was half the thickness of a human hair, and that was what's caused it. No, excuse me, no. Not unless it's a piece of glass or a piece of ceramic, okay, that's very, very brittle. You can quantify these things, and I sort of make part of a career out of reading other people's reports and where they don't quantify anything at all, and then destroying their theory by just putting some numbers on it. For example, I have last week I had an oxygen cylinder that blew up. The guy opens up the brand new oxygen cylinder, turns the valve, kills himself. First of all, you have to have fire. You have to have ignition, right? To get this explosion. It's an oxygen tank. Oxygen doesn't burn. Where did the fuel come from? Well, first you have to look at the fracture patterns on the whole thing and say, well, did it fail from the inside or the outside? Well, in this case, when the whole cylinder wall of this, 250, this 5-foot high oxygen cylinder is laid out flat. It used to be a cylinder, and now it's got fractures down the entire length and then around the base and coming back up. The whole thing failed from the inside. I can tell, because when you flatten it like that. Now, how did I flatten it like that, you might ask? Well, a regular cylinder is 2200 psi, is the pressure of the, in a full cylinder. There's a safety factor. It takes something over 3 times that pressure, 6,000, 7,000 psi, to actually rupture one of these tanks. And they put enough safety factor on it so something won't happen. hopefully. But clearly this thing saw, to open up like that, some pressure of 6,000, 7,000, 8,000 psi. Well, where can you get that? Well, you can get that from an explosion, okay? How do I get an internal explosion in an oxygen cylinder? Well, we'll talk about that in a second. But you also know certain things about how fast the crack can run. Because the crack ran down 5 feet, around, and up 5 feet. So it ran about 10 feet before, and the gas was still opening it up. Well, how can the crack grow so fast without the gas getting out? Anybody have an idea? You never learned about decompression velocities? A crack can run approaching the speed of sound. It's limited to going no faster than the speed of sound. Okay? The speed of sound in a cylinder or in steel or most metals, most solids, is on the order of 15,000 feet per second. Okay? You actually can get that by things that you should know. Let's see if I can remember how to do this. It's actually, you know that the distance between atoms is about, let's say, 2 times 10 to the minus 10 meters, right? 2 angstroms. That's 2 angstroms, right? So that's the distance between atoms. And another thing you're supposed to know is that the vibration speed of atoms is about 10 to the 13th frequency. You knew that, right? If you're a material scientist, you know that. You did know what an angstrom was, right? And you knew that atoms are about 2 angstroms apart. So anyway, well, some of you did, some of you didn't. So I've got a distance and a frequency, and frequency has units of time to the minus 1/2, right? So if I multiply these together, I get 4 times 10 to the 3rd meters per second, right? That's the velocity of sound in steel, or aluminum might be 3,000, you know, but it's about that, it's on that order. Actually, I looked it up, it's 3,600, no, I'm sorry, it's 5,200, okay? But, you know, they're not exactly 2 angstroms apart, and the frequency, the Debye frequency is not exactly 10 to the 13th, you know, 2 times 10 to the 13th, it vary a little bit. But order of magnitude, you're talking several thousand meters per second. So it works out to about 15,000 feet per second. Well, if it were going at the speed of sound, how long does it take to go 10 feet? It takes 2/3 of a millisecond. Now, what's the distance of separation of gas molecules? We're going to go through estimation today here. Being estimated, that's about right. Right, Barry? Exactly. It does depend on the pressure. How, you know, gases expand with pressure. At room temperature, typical gases will have about 500 times the volume of the solid. Okay, that's just kind of a rule. I often use 1,000. And your 100 angstroms, if I take well, actually, I have to take the cube root of this. Okay, because that's a volume. To get the linear dimension of separation, I have to take the cube root of that. So it's about 8 atomic distances, or 16 angstroms. So your 100 wasn't too far off for a guess. At least someone gave me a guess. But if it's 1,000, then it's 10 atomic distances. That's at standard temperature and pressure. You know, if I took methane at room temperature and I looked at liquid methane, and, you know, liquefied it, then it would have about 1/500th the volume. Liquid methane to gaseous methane at room temperature. Now, if I'm at 4,000 degrees, then it's got a much higher volume. So you're absolutely right. So you're right, and you're right too. Which I can now tell you the story about this Joel Moses, who used to be provost, used to like to tell this story. And this is the one about the rabbi who had 2, and Joel's Jewish, so it's okay to tell the story if you're Jewish, and I'm just telling what he told. So the rabbi has 2 people who are disagreeing with each other, and they come in to talk to him, and so he sits down, listens to the first one, and he says, "You're right." And he listens to the other one, and he says, "You're right." And his wife, who's listening to all this, says, "But Rabbi, how can they both be right?" He says, "You're right too." it turns out that's often the case, that it is possible to have multiple people right at the same time, even if they seem like they're disagreeing. Anyway, so the distance of separation between gas molecules is 8 to 10 times as great as it is between solids. And therefore, the velocity of sound in a gas is about 8 to 10 times less. And what's the velocity of sound in air at sea level at standard temperature and pressure? Feet per second? You must be talking feet per second, because 343.6 meters per second, or whatever that number is, okay? There actually is a standard number. But it's approximately 10 times less, because the atoms have to go 10 times as far to knock into each other. Anyway, so getting back to the cylinder that split. So what happens in a cylinder splitting like that is the crack runs faster than the gas can decompress. So that's a cylinder. What about a gas pipeline? Now, an oil pipeline is not quite so bad, because the oil pipeline, you have a fracture in an oil pipeline, and you got a liquid oil inside, and the liquid, what's the difference in separation? You know, it's like 10–20% less than the speed in the solid, right? Because the atoms are close together. So what happens in an oil pipeline, if you have a rupture, is the crack starts and it stops not too far away, like 1 or 2 diameters of the pipe away. Why? Because the liquid is decompressing just as fast as the crack is running, or faster. I mean, I said the fastest the crack can run is the speed of sound. Typically, it only runs about half or 2/3 of that. It doesn't get up to full speed, full theoretical speed. So basically, in a liquid pipeline, if you have a rupture, it ruptures and you get a fracture that's 1, 2, 3 diameters long. In a gas pipeline, on the other hand, you can have a rupture, and they've had gas pipeline ruptures that go for 30 miles because the gas is not decompressing ahead of the crack. Because the gas stays under pressure, because it decompresses at 1/10 the rate that the crack can be moving. So they have had pipelines that have had 30-mile cracks. It can ruin your day. So what do? They actually put crack arresters in and things like that. So when people talk about building a gas pipeline in Alaska, and we've got the oil pipeline, and people say, well, why don't we just put gas down the oil pipeline? Two different animals from a fracture point of view. And the gas pipeline is built to more stringent standards, has to have crack arresters and things like that, whereas the liquid pipeline doesn't have to have that. So anyway, we get back to this tank, and so it clearly pressurized from the inside. Now the question is, well, where did it come from? Well, one theory on one side was when they filled the tank, they got some oil or grease or something inside there, and it ignited. Well, it turns out people know that oxygen, when you turn on a cylinder, the oxygen can ignite. The reason it can ignite is you've got this high pressure oxygen in the cylinder, and you got a regulator right here, and the regulator has low pressure in it, right? On the back side before you open the valve. And what happens is the high pressure stuff comes slamming in to this low pressure region on the high pressure side of the regulator to pressurize it. But as it does that, the gas coming out gets recompressed by the momentum of the gas behind it, and you can reach theoretical temperatures of 1700 degrees Fahrenheit. People have measured temperatures up to 1000 degrees Fahrenheit. If you open the valve quickly and the gas comes rushing in there, the heat of compression will give you a temperature spike. Now, it's very localized, it's a very small mass, but you can, if there is something there, you can ignite it. Well, if I ignited it right here, I'd blow up the regulator. That wouldn't blow up the tank. So I actually had to have fuel that was down inside the tank if I got something here. Now, so one side says, oh, you screwed up, you got fuel inside the tank, and when the guy turned it on, it wouldn't have happened. And they said, oh, if we had done that when we were filling it, we would have blown ourselves up. That's not true, because you fill it over about a half an hour or 45 minutes. They actually go around and feel the sides of the tank, because they're compressing this as it goes in. If you try to fill up the tank too quickly, it could overheat. So you actually do it much more slowly, and the temperature rises much, much less. Typically takes 700 to 800 degrees to ignite a hydrocarbon. Okay? So the other side says, no, it wasn't internal. It was the regulator blew, and I had an oxygen flame impinging on the wall of the steel tank. And we know this whole thing occurred in about 2 seconds because there was one guy who survived, and he had asked the other guy to go turn on the oxygen tank. This other guy was underneath a cement truck, which is one of the reasons he survived. And he saw the guy walk over. He could see the feet because he was on a creeper under the truck, and he knew it was only like 2 or 3 seconds before the explosion occurred. So there was only 2 or 3 seconds that this thing could have occurred. So they're saying, okay, this flame shot out here, it externally heated it right here, and that's what caused it to blow. You believe that? You think passing a gas torch for 2 seconds on the surface of a tank is going to cause it to blow? Why don't you believe that? You don't believe that because you can run your finger through a flame, right? As long as you do it quickly and not burn yourself, right? It's a certain thermal time constant, right? You've all done your finger through a candle. You ever done it through a propane torch? I've done it in class here for students to show them. Yeah, I go a little quicker with propane torch, but okay. But I mean, you can go at that speed. You know, you don't have to go like that. You know, you can go like that. I've never tried to go like this. But so anyway, it turns out you can quantify that. I happen to know, and you're going to learn later in the course, that an oxy-acetylene flame puts out 1,000 watts per square centimeter impinging on the surface. I know that if I have to triple the pressure of this gas, I know there's 300 moles in 250 standard cubic feet, 300 moles of gas, and I want to triple the pressure. It starts out at about 300 Kelvin, and I want to triple that, so the delta T is about 600 Kelvin. Okay, this is delta T, this is N, and what else do I need to know the change in pressure and volume? nRT, right? And R is 8.3 joules per mole Kelvin, and that works out to 1.5 million joules. So to heat up the oxygen in here to a pressure sufficient to do this is 1.5 million joules. Okay, so, and I can put in, well, let's say I have a big flame here. It's not just one square centimeter. Let's say I have something that's about 2.5 inches in diameter. That's about 10 cubic centimeters. So instead of 1,000, I got 10,000 watts, okay, going into that tank wall. 10,000 watts over 2 seconds? How many joules is that? 20,000 joules. I don't think they quite made it, did they? So it's pretty easy to show that the external theory is bogus. You can also show it's bogus because this is a 1/4 inch thick wall, and you can estimate how long it takes for the heat to penetrate the wall. Turns out it's about 10 seconds. We'll learn that later in the course, how to estimate that. The point is, you actually can estimate these things. You can put numbers on things, and you can tell the difference between 2 theories in a failure analysis. But let me tell you that there's only about 1 person in 1,000 out there who ever does. Most people just get up and pontificate. Okay? Well, sure, it's a stress concentration. We all know stress concentrations are bad. Well, okay, but how bad is the question? And sometimes you can explain it with stress concentration, sometimes you can't. Okay, so that's enough on that part of failure analysis. Any questions? Let's talk a little bit about residual stresses. All this stuff I said about stress concentrations and stress intensities and stuff, if you go and you do all the analysis and you try to put the numbers on it and you still can't explain it, you invoke residual stresses. Okay, that's the final out always. Oh, there must have been residual stresses present, and that's a great one because it's very hard to quantify. Okay, what the residual stresses are. However, they exist. They're induced either mechanically or thermally. If I were to take a paper clip and bend it and then kind of straighten it back, there would be residual stresses in there, mechanically induced. If I were to take it and heat it with a torch and keep it restrained while I did it, there would be residual stresses. Residual stresses can be good or bad. When I temper glass, one way to temper glass, if this is the thickness of a sheet of glass, while the glass is cooling down, if I blow air on it and cool the surfaces of the glass more quickly than the inside of the glass, what type of stresses will I get on the surface as it's cooling down? If this cools more quickly on the surface, it shrinks. Well, initially while it's cooling, this is in tension because the outside's shrinking more than the inside, but it's all connected together, right? So this stuff goes into tension when I cool it quickly, and the inside goes into compression. That's when it's hot. When it cools, it always reverses. Okay, and you actually have to kind of go through the whole thing. When it's in tension, on cooling, when it's cooling but it's still hot, if I take a little square, if it's in tension, that little square becomes elongated, right? If I have one here and it's in compression while it's hot, it becomes compressed, right? Now I put something together like this and like this when it gets down to room temperature, but in fact they have to have the same length on this edge because they're all tied together, right? So what do I have to do to this at room temperature and this in order to get them to form a big square that's all one solid piece of material? I have to put this one in compression and this one in tension. So the residual stresses are compressive on the surface when it's cooled down and tensile in the center. Whereas when it's cooling, it's exactly the opposite. What happens is I yield the material here and change its shape, but when it's all said and done, they never really change their shape except on a microscopic scale, and they're all bound together, and I'll have residual stresses. And the easiest thing for me to always remember, and I've gone through and analyzed a number of them, and it's never failed. Whatever the stress state is when it's hot, you will have the exact opposite stress state when it's cold. Okay? So that's for glass, and that's called tempering of glass. You're changing the way it cools on heating or on cooling. So you cool this faster than this. You end up with the compressive surface stresses when you're all done. And compressive surface stresses are good because I have to overcome the compressive stress on the surface in bending before the glass is going to break. So the glass, you can actually, I don't have it, but when I was a student, Professor Ullman, who's now at Arizona, had a piece of glass. It's actually chemically tempered. I'll tell you what that is in a second. It had a bow in it about 3 or 4 inches high, and you could just put it on the table and just flex it like a spring. Okay, just flatten it. And he used to do it without gloves on. Anyway, it's because it's chemically tempered. With chemically tempered glass, you basically take a glass that has lithium in it, and lithium is a small ion, and you chemically exchange the lithium with sodium and potassium, which are larger atoms. And so you mechanically stick heavy atoms in on the surface, and that puts compressive stress in. Okay? So you're kind of stretching the, it's not a lattice here, but you're stretching the bonds, or compressing the bonds. So you can chemically temper or thermally temper glass and get favorable compressive stresses. That means that if you're going the other way, if the outside were hotter rather than cooler, you could end up with very unfavorable stresses, tensile residual stresses on the surface. Now, residual stresses occur in welding all the time. In fact, the problem is that in welding, if I have a fairly thick section weld, let's say it's a couple of inches thick, and I put a weld in here, and I put another pass, another pass, another pass, what will happen is this metal shrinks because there's about a 4% volume change when the metal solidifies. I put one pass in here, and that's not so bad, but when I put this pass in here, it's restrained by this pass here, which is already solidified. and I put this one in, it's restrained by these two. And as I build up bigger and bigger, I will end up, the whole plate wants to change its shape and be bowed. And I'm sure you guys have, most of you have seen distorted welded plates. Okay, so you get a distortion. If it's a very rigid structure and the thing's tied together and it can't distort, you end up with residual stresses. So it's welding is a trade-off, or welding residual stresses is always this trade-off between distortion and residual stresses. If you allow it to flex, it can distort, you won't get big residual stresses, but if it's heavy and it can't flex, you'll get big residual stresses. It turns out the residual stresses in very thin sheet, like 1/8 of an inch or less, are not very great because the sheet, for most geometries and thicknesses and distances, has enough compliance that it flexes. And well, you don't get big residual stresses, you don't get big distortion either. In heavy plate, you get heavy residual stresses. It turns out the worst distortion occurs at about 3/8 of an inch, about a centimeter, and you can prove it various ways. But your maximum distortion is about a centimeter thick. And for all those of you who are surface ship guys, how thick's the hull? About a centimeter thick, right? So it's a big problem. Whereas submarines, which are thicker, and I can't tell you, because we don't know, right? What the thickness of a submarine hull is, but it's considerably thicker, you end up with very heavy residual stresses from the welding operation. The ASME boiler and pressure vessel code says that once you get a weld that's more than 1.25 inches thick, you have to stress relieve it. You cannot put a pressure vessel into service without stress relieving it. And the reason is, somewhere around this thickness, you're going to get the maximum possible residual stresses, which are equal to the yield strength of the material. Okay? And that means if I put a very slight fatigue load, or a very slight load on something that's already got yield level tensile stresses on the surface, I could get fatigue cracks, right? Even though it's lightly loaded in terms of service stresses, the residual stresses could kill you. So, now I ask all you submariners, why don't we stress relieve the hull of the submarine? Or do we? We do. You don't put it in a big furnace, although for pressure vessels, they have furnaces that are 10 times the size of this room, and they put a whole pressure vessel in something. When do we? The heater is for preheating the steel to keep the hydrogen off. To stress relieve steel, you've got to go to 11 to 1200 Fahrenheit. That's when the steel starts to soften, lose its strength, okay? And that's when you can relieve the stress. Springs, they can stress relieve at 550 degrees Fahrenheit, but they're a different animal. They got stresses, they've got yield strengths of 300 KSI. And so you can stress relieve them at lower temperatures. But no, we do stress relieve submarines, but we don't do it thermally. How do we do it? We do it mechanically on the first dive, right? Right? The pressure of the first deep dive causes compressive stress relief. You can mechanically stress relieve something by just pulling on it. In fact, most high-strength aluminum alloys, heat-treated aluminum alloys, have to be stress relieved. I showed you that little washer from the helicopter that failed because of residual stresses. It was supposed to be stress relieved. If you go to the Alcoa plant in Davenport, Iowa, which has the world's largest rolling mill to roll plate, and this is the plant where almost all the aircraft wing plate comes from, and certainly in the United States for Boeing, and well, we used to have multiple airplane builders in the United States, but anyway, comes out of this plant. And they have a huge machine, both sides of it are about the size of this room, and it can grab a plate 3 or 4 inches thick after it's been heat treated, and they stretch it 1 to 3%. Because the heat treating process for aluminum requires that you heat it up and then quench it and then temper it. And that whole quenching process in a thick plate does the same thing it does to the glass, except, yeah, it may be compressive on the surface, but it's tensile in here. And if you're going to machine away part of that to make an aircraft wing, you could be getting into all kinds of problems of distortion on machining when you machine stuff away, but you could also get into problems with stress corrosion cracking because it's got residual stresses left in it. So they actually they have a temper. If you go to, let's say, 61 T751 temper. Most of you may have heard of 6061 T6 temper. 6061 is a particular aluminum alloy. T6 temper is the heat treated and aged to give it precipitation heat treated and aged to give it like double the strength it would have if it wasn't heat treated. T7 is a slight overage, and the 51 means 1% elongation. Okay, the 5 is in there for something else. I can't remember why, but I think it's, I can't remember. But it means that they actually stretch the plate 1% to relieve the residual stresses. That washer was supposed to be, I don't remember, 6061. They had on the drawing T751, but in fact, how do you stretch a washer in the axial direction? How do you grab it? There's something else called T73, and the 3 means that you squeeze it 3%. You compress it 3% to stress relieve it, which is what they should have done with the washer, but they didn't do either one. That's why it had residual stresses, that's why it cracked. So, by stress corrosion cracking. So, it turns out every time you deep dive on a submarine, you're doing a little bit more stress relief, mechanical stress relief. Other times, on some vessels, pressure vessels, they hydrotest them. And they go up to 1.5 times their rated stress, and they basically stretch it by internal pressurization with water. Okay? And you're stress relieving when you do that. So there's lots of times where we're doing stress relief. It's not always thermal stress relief. This is the important thing to remember. If you don't stress relieve, I told you about the washer. The first example ever, or first time anyone ever understood or explained stress corrosion cracking was in World War I. The shell casings that were made out of brass were cracking before they had fired the shell. You know, you've got the shell casing, and then you've got the penetrator, the point, and this thing was squeezed, the brass was squeezed down on that and had the charge inside the brass casing. And they were finding little cracks before they did anything. Well, it turns out brass that has residual stresses from that crimping operation is susceptible to stress corrosion cracking in ammonia atmospheres. Where's the ammonia come from? It comes from the explosives, the other things that are being fired off, right? Ammonia is one of the products of combustion of the explosives. And so the ammonia in the air was attacking the shell casings once they got them out to the trenches. There was no ammonia in the factory, there was no ammonia in the warehouse, there was no ammonia on the ship getting it over there. But you got in the trenches, and there was ammonia from the other explosives, and the shells were getting to be no good. And that was the first understanding of stress corrosion cracking. Some materials, there's a mercury iodate that you can put on brass, and you put 1 drop on and it cracks immediately. I mean, it just snaps by stress corrosion cracking. Other cases, stress corrosion cracking can take years. Not the 3 Mile Island plant that had the accident, but the sister plant got shut down for 2 years while they were investigating the first one, and they went to start it back up, and it's running now. But they had a $30 million steam generator, you know, a bunch of tubes inside a pressure vessel, and in the first 2 hours of startup, because of the oxygen in the water, the nickel tubes, stress corrosion cracked. They only did about $10 million worth of damage. And after they rebuilt that, then they could start up again. So stress corrosion cracking, residual stresses are sort of insidious, but they keep on showing up. Okay, that's enough for now. We'll take a 5-minute break and come